This video is about derivatives of power functions and polynomials. Of course, polynomials are certain types of power functions, but power functions are more general. For our notes, we'll say this: if n is any real number, c is a constant, and f and g are differentiable functions, then the following are true. First of all, we'll say this: the derivative of, when we say d over dx, remember that means derivative of x to the n power is equal to, notice what's happening here, it's n times x to the n minus 1 power. So this exponent that was originally there, n, gets thrown down in front, and then we decrease that original power by 1 for the new exponent. So this rule is really a shortcut to the whole limit process of finding a derivative. This rule can be proven fairly simply with the limit definition of a derivative. Usually that's displayed quite nicely in a textbook. Secondly, we'll understand that if you take the derivative of c, remember c is our constant, so c times a function f of x, then that c value can end up out in front of the derivative. In other words, you take this constant and just throw it out in front of the derivative. It does not affect the function in that way, and the derivative of the function will just follow after it. And thirdly, if we take the derivative of a sum or difference of functions, so f of x plus or minus g of x, then we can take the derivative of each function separately and then add or subtract the results. So the result would be the derivative of f of x plus or minus the derivative of g of x. Let's try some examples where we want to differentiate each function. Our first example is given as v of t equals t to the negative 3/5 power plus t to the 4th power. Now this qualifies as a power function. Of course, because of the first term having a rational exponent, the negative 3/5, this would not qualify as a polynomial, but it is a power function, and so we can use the rule we cited above. The derivative, which we'll write as v prime of t, using some of our derivative notation there, is going to equal, now to use the rule, remember it's stated above that we take the exponent or the power of t in this first term, the negative 3/5, we throw it down in front of the t. So that'll be a negative 3/5 in front of the t, but then we decrease the original power by 1. Now it was a fraction, negative 3/5. If we're going to decrease that by 1, of course we'll use a common denominator of 5/5. So really it's negative 3/5 minus 5/5, which would give us negative 8/5 plus, and then for the second term, which was t to the 4th, we use the same rule, which is throw the power of 4 down in front to make it 4t to the, and then decrease that power by 1 to get third. Now you may see some variability in how textbook authors prefer to finish or simplify answers, but you probably would not see many authors who would leave this as it is right now. So typically we want all positive exponents, and often authors will also want common denominators if there are multiple terms. So let's take this a little bit further. If we rewrite v prime of t here and you convert this negative exponent to a positive one, we'd have negative 3 over 5t to the positive 8/5 power as the first term, plus, we'll just keep our 4t cubed for the second term. And then as you can see, we have two terms. One of them has a denominator. So if we wanted to put this into a combined fraction with a common denominator, which again many authors would do, or some authors would do, we can go ahead and utilize the one denominator we have as the common denominator, so 5t to the 8/5. And then in the numerator, we have this negative 3 that was originally above that in the first fraction that would have to stay. But in the second term, we would have to turn its original denominator, which was 1, into this new denominator, which means we're going to have to multiply the numerator by this 5t to the 8/5, which means the new numerator would be 20t to the 23/5 all over the LCD. So this is now written with a common denominator. There's actually good reason to want to take it this far, as will be evident later on. But for now, just check with the back of a textbook to see how the author prefers it, and this might be what they want with the common denominator. Also, you might also see that they switch the top term so that the negative isn't out in front. That's just a minor switch here. So you might see a final answer as really this one, or even the previous step, but the last one you might see is 20t to the 23/5 minus 3 all over 5t to the 8/5. And so we would say that's v prime of t. Let's try a second example. This time our function is f of t equals, and then in parentheses we have 2t minus 3, and then on the outside of those parentheses it's being squared. Now, if you try to apply the power rule we have written above in our notes to this one, it doesn't quite fit. So notice the base of this function. If you consider it as, a base to some power, the base would be this 2t minus 3, and the power is 2. Well, it doesn't quite fit the rule which has a base of only one single variable. In the rule it was x, it could be a t as well, but the point is that rule works when the base is a single variable, not an expression like 2t minus 3. Now, there is a way to handle something with this kind of base, but that's a later rule, so more coming on that. So in order to use the rule we have right now above, what we're going to do is first just expand this function. So when we see 2t minus 3 all squared, of course we know that means 2t minus 3 times 2t minus 3, and we can FOIL that together, which would end up giving us a 4t squared minus 12t plus 9. Once expanded, now you can see that this has really multiple terms to it. And then if you go back up to one of the other properties in our notes above, you'll recall that when you're taking the derivative of some kind of function that has multiple terms like this, you can, and they're all being added or subtracted together, you can take the derivative of each term. And so what we'll say here is now we're going to switch and call this f prime of t, now that we've expanded our function to the way we want it. And to take the derivative, we'll just go one term at a time using the power rule as applicable. So for the first term, 4t squared, we'll take the power of 2, multiply it down in front. 2 times that 4 that's already there would be an 8t to the, and then decrease the power by 1, which would give us just a t to the first, which you wouldn't even write the first power there, you don't have to. And then in the second term, we have negative or minus 12t. If we apply the power rule to this one, we'll keep the negative. The power of t is really a 1. If you throw that 1 down in front, 1 times negative 12 is negative 12. And then t to the 0 would be left, but t to the 0 is really just 1. And so we're going to rewrite that one more time to convert it. I'm going to leave the t to the 0 just for the moment so you can see that what's happening there. And then lastly, of course, if you have a constant, this in the same rule will just turn into a 0. The derivative of a constant is just 0, and that can be a separate property on its own, or you could kind of force the power rule into that. If you imagine that there's a t to the 0 already there with the 9, that rule would also yield a 0 for that term. Now we can simplify this derivative one last time and say f prime of t is really going to be 8t minus 12. Let's try a third example. This one reads y equals, and then this function is a fraction where the numerator is the square root of x plus x, and the denominator is x squared. Now, in the numerator, those are separate terms, the square root of x plus x. And so what we're going to do in order to be able to utilize the only rules we have above so far with derivatives, and yes, there are more rules coming that could apply to this function, but with what we have now, what we're going to do is simply split this up into multiple terms. So as you know from algebra, you could reduce or rewrite, you could say this function as the square root of x over x squared plus x over x squared. So you're giving each numerator term its own denominator here. Now the reason we might care about this is because you can even take this further and write each of these terms as a single power of x. Again, recall some algebra with this. If I take the first term, which is the square root of x over x squared, remember the square root of x is really x to the 1/2, which means if I were to bring this x squared up to it, I would have x to the negative 3/2. And then in the second term, I'll have plus, instead of x over x squared, yes, that's 1 over x, but we're trying to bring everything up to the same level here, so we'll call that x to the negative 1 in the same way. Now that we have it written with single terms that are really power functions, right? These have exponents that are real numbers. This is not a polynomial because they are not natural number powers, but they are real numbers, so they qualify as a power function, which means our rule above works, which means we can say y prime equals, if I take the first term, the x to the negative 3/2 power, throw that power down in front, I'll have negative 3/2 x to the, and now I'm going to decrease that original power by 1. So remember, 1 with a common denominator with this original power would be 2 over 2. So it's really negative 3/2 minus 2/2, which would be a negative 5/2. And then moving on to the next term, we'll say plus. But then this power of negative 1 would come down in front and make a negative 1 there. So really we should say minus 1 times x to the negative 2 power to use that rule. Now we'll do some simplifying like we had done in a previous problem where I'm going to convert these negative powers to positive ones and then possibly need a common denominator here. So the first term, which was negative 3/2 x to the negative 5/2, would be negative 3 over 2x to the positive 5/2, and then minus, and then our next term was x to the negative 2, so really that's 1 over x to the positive 2. And then we'd want a common denominator with those two terms, which would be a 2, and then we'd want to use the highest power out of those two options. So we have x to the 5/2 and x squared. We want to use the greatest of those because we can always build the other one up to match it. So we'll say x to the 5/2 as our power of x for the denominator. Okay, now we have to do some adjustments, at least in the second fraction. So if we look at the first one, it already had this common denominator, so the numerator there could just stay as a negative 3. Moving on to the second fraction, though, it was just an x squared, which means it was missing the factor of 2, so we'd have to multiply that fraction top and bottom by 2 to make up for that. And then we had x squared, but we need an x to the 5/2. So remember when we decided about this common denominator, we said to use the bigger power of x because we can build the other power up to it. Well, this is what we mean here. So when you take x squared, what would you have to add to that squared to get 5/2? Well, 5/2 is really 2.5. If I already have 2 as the power, I'd have to add a half, which means I'd have an x to the 1/2 that would also have to throw in to make up for it, which means this new numerator is now going to be minus 2x to the 1/2. And at least now we can say that this denominator is adjusted to be 2x to the 2 plus 1/2, which is 5/2. And so we have it all matching. So you could rewrite this one more time as, now notice in the numerator both terms are negative. You could even factor out a negative. There's a little variation here on how to type the answer, or write the answer, but you could say negative, and then I could make this 2 square root of x plus 3. So I'm factoring out the negative in front, and I'm turning the x into a square root. Or you could just leave it as x to the 1/2. Either way is okay, really. And then the denominator would be 2x to the 5/2. And so this is one valid form of the answer. You know, different textbooks or instructors may get a little more picky on converting the rational powers to roots, but this really is correct. Let's try another example where this one says, find a parabola with equation y equals ax squared plus bx plus c. Okay, that's just a general quadratic parabola equation here. That has slope equal to 4 at x equals 1, slope equal to negative 8 at x equals negative 1, and passes through the point 2, 15. All right, so there's a lot to put together here. Let's kind of identify these key pieces here that we were given here. Slope equals 4 at x equals 1. What does that mean? Well, when you see language like the slope of this parabola, really that's what that means. A parabola is a curve, right? So when you say the slope of the parabola, you're really talking about the slope of the tangent line to it at some place. First of all, instead of using y, I think it's more convenient to use the function notation. So we're going to call it f of x. Really, this means that f prime of 1, right, the slope at x equals 1, that's the derivative at 1, equals 4. That's what we were given here. Secondly, they said the slope equals -8 at -1. Well, okay, in the same way, we could say f prime of -1 equals -8. And lastly, this passes through the point 215, 2 comma 15. So, all right, let's unpack what we have already a little bit more. First of all, if this original ax squared plus bx plus c is what f is, then f prime will be its derivative. Well, this is just a polynomial function, which means the rules way above we had in our notes for this video will actually apply to take its derivative. So we could say, first of all, let's write this on the side here. So y prime, which of course equals f prime of x, the way we've been using function notation here. In this, given ax squared, that term would turn into a 2ax. If you take the power of 2, throw it down in front, and multiply it with the a, we get 2ax. And then for the next term, when it was bx, remember the original power of that x is a 1. If you throw the 1 down in front, you'll just get a plus b, but then it would be x to the 0, which wouldn't even show up. So really, if the general function is ax squared plus bx plus c, then the general derivative is 2ax plus b. That's just using the derivative rules above. Of course, that last term is just a constant c. As mentioned earlier, that will turn into a 0. If we take these two facts we've already written down, the first one being that f prime of 1 equals 4, now that we know what f prime is, we can find f prime of 1. So we're just going to plug 1 in for x in this prime form of our, well, the derivative here. So this would be 2 times a times 1 for 2ax plus b must equal 4. That's f prime of 1 equals 4, just as which is what we had already established that they gave us. Secondly, we could say that 2 times a times -1, so now this is f prime of -1, and then plus b, but this one equals -8. So again, f prime of -1 equals -8. We're just plugging in that information to the prime form or the derivative that we've already calculated. Now let's recall the whole point of this problem, which was find a parabola with this equation. So in other words, we need to understand what a, b, and c are, and if we do, we just plug them in and we have our answer. What we're getting to here is a system of equations for a and b. If we rewrite this maybe a little bit cleaner, this would be the same thing as saying 2a plus b equals 4, and -2a plus b equals -8. And then actually this is set up perfectly for some elimination. If we just add down, these a terms cancel, giving us 2b equals a -4, which means b would be a -2. And so there we have it. At least so far we found one of the values. Remember, we want to find a, b, and c. We just found b. And as you know from the process of solving a system, if you know b in this same system, you can go back and find a. So we'll go ahead and take one of the original equations we had here. I'll pick on the first one since it was more positive here, but we had 2a plus b, but we just found that b is really -2, equals 4. And so if I solve for a here, I'll have 2a equals 6, which means a equals 3. So now we had found b, we just found a. This is where next, and lastly to find c, we're going to have to go back and use that piece of information we haven't touched yet. Remember we said that this passes through the point 2 comma 15? So what we can say is that f of 2 equals 15. Well, f of 2 would be like saying, okay, it was ax squared. Well, that's 3x squared since a was 3. Ax squared plus bx. B is negative 2, so really we could say minus 2x plus c. That's f of x so far, but we know that f of 2 is 15. So we could say here so far f of x equals this, but then 15 is what we get when you plug 2 in for x. And so if we simplify this just by getting c alone, we'll end up getting c equals 7 here, which means in summary we could say y or f of x equals, remember we're trying to find this quadratic parabola in the form of ax squared plus bx plus c, but now we just found a, b, and c, so we'll just put them in place. We'll say 3x squared, that's ax squared, minus 2x, that's plus bx, and then plus 7 because that's plus c. So there's our parabola.